Hi, my name is Sienna Weens, Process Safety Engineer at Resource Compliance. In this short video, we will take a deep dive into an important component of an ammonia refrigeration system, compressors. In this video, we'll explore a variety of topics related to compressors. First, we'll discuss the function of a compressor within a system. Then, I'll show examples of various compressor types. In items 3 through 7 in this list, we'll consider how to properly document compressor specifications within the Process Safety Information section of a PSM program. Finally, we'll conclude by reviewing recognized and generally accepted good engineering practices for compressors. Namely, we'll highlight any unique requirements in IIAR standards 2, 4, and 6. The purpose of the compressors is to raise the temperature and pressure of the low-pressure gas in order to reject the heat absorbed in the evaporator to the atmosphere. The compressors receive low-pressure vapor from the main suction accumulator or recirculator and discharge high-pressure vapor to the evaporative condensers. Under normal conditions, the compressors contain both high and low-pressure vapor ammonia. There are several types of compressors used in ammonia refrigeration systems. These include screw, reciprocating, and rotary vane compressors. The screw compressor type is shown here. The screw portion of the compressor is installed on top of an oil separator and driven by the adjacent motor. There are two types of screw compressors, rotary screw and single screw. The rotary screw functions by drawing gas into the interlobe space between adjacent lobes. Next, the gas is trapped between rotors as they spin and mesh together. This rotation causes compression of the gas until it reaches the outlet port and is discharged into the oil separator. Single screw type of compressor is manufactured by Vilter. This video describes how the single screw operates.
Meshing with the main rotor are two Stargate rotors. The teeth of the gate rotors intermesh with the flutes of the main rotor, closing the gate and trapping the gas in the flutes. The gate rotors are identical in size and shape and are positioned on the opposite sides of the main rotor. As the teeth travel through the flutes of the main rotor, the trapped gas is compressed to a higher pressure and discharged radially out through the discharge ports of the compressor. Vent holes through the main rotor allow both ends to be at suction pressure for balanced axial forces. Dual gate rotors allow compression to take place on both sides of the main rotor, which results in balanced radial forces.
Another common compressor type is the reciprocating compressor. The reciprocating compressor functions in a similar manner to a car engine. Pistons inside the compressor draw low-pressure vapor into the compression chamber through an intake valve. Once this valve closes, the piston moves upward, effectively compressing the gas. At this point, the discharge valve at the top of the compression chamber opens, which allows a high-pressure vapor to exit the chamber. The third and most rare type of compressor is the rotary vane. The rotary vane compressor functions by drawing vapor in through the right side of the compression chamber. The blades inside move the gas to the left side of the compressor, where the available space becomes smaller and smaller. Finally, the gas exits through the outlet port on the left side of the compressor. Three of the most relevant operating limits for compressors are pressure, temperature, and oil level. The discharge pressure of a compressor can be determined at its microprocessing panel or at a physical pressure gauge installed on the compressor discharge line. This discharge pressure should not exceed the maximum allowable working pressure of the oil separator or the relief valve set point. To ensure this, the compressor is equipped with a cutout which will shut the compressor down once it exceeds a certain set point. The discharge temperature of a compressor can also be determined at its microprocessing panel. If a panel is not installed, some reciprocating compressors are equipped with a temperature gauge which indicates the discharge temperature. The oil inside a compressor provides lubrication for the moving parts. Therefore, it is important to ensure the oil is maintained at a certain level. Screw compressors are typically equipped with this set of sight glasses. On the left, these sight glasses indicate the level of oil available for use inside the compressor. When a compressor is running, the bottom sight glass will typically appear full and top sight glass will be empty. When the compressor is off, the top sight glass is usually half full. The sight glass on the right is located on the downstream side of the coalescer. If oil appears in this sight glass, it means that oil has leaked past the coalescer where it can now travel through the rest of the refrigeration system. If a noticeable amount of oil is observed in the right sight glass, this is an indicator that the coalescer gasket needs to be replaced. A reciprocating compressor typically has one sight glass, which is located at the bottom of the crankcase. During normal operation, this sight glass is typically half full. When documenting the materials of construction for a compressor, the key document is the manufacturer data report associated with the oil separator. The manufacturer certified drawing is another key document to have on file for materials of construction. The P&IDs typically display the three types of compressors in three different ways. Screw compressors are typically configured in this manner, with a trapezoid representing the screw portion of the compressor package. Reciprocating compressors are usually drawn to indicate how many cylinders are present. This information allows you to determine the number of cylinders or compression chambers that are present in the compressor. Lastly, this P&ID depicts a typical configuration for a rotary vane compressor. As it relates to compressors, there are a number of safety systems and other appurtenances to be aware of. The safety cutouts are an important component of any compressor as they protect the compressor from internal damage and prevent the discharge pressure from reaching an unsafe level. The cutouts for the screw compressors are adjusted on the associated micropanel. Reciprocating compressors that are not equipped with a micropanel have a type of electromechanical switch called a pen switch. These switches are shown on the right. The set points can be adjusted with a lever or wheel on the side of the switch. Reciprocating compressors are not usually equipped with temperature cutouts, while screw compressors are equipped with discharge, suction, and oil temperature cutouts. Various components of compressors are required to be equipped with a relief valve. External relief valves can be seen installed to protect an oil separator, a reciprocating compressor, or a combination of the oil separator and screw portion of a compressor. Internal relief valves cannot be seen without disassembling the compressor. Filter reciprocating compressors are manufactured with an internal safety valve, which provides overpressure protection to the compressor. Hydrostatic relief valves are used when the equipment contains liquid. This type of relief valve typically discharges back into the system instead of to the atmosphere or diffusion tank. Hydrostatic relief valves are often installed to protect oil coolers from overpressurization, as seen in this picture. Compressor packages are equipped with several nameplates. A screw compressor can have as many as 6 nameplates, and a reciprocating compressor may have up to 4. For example, a Frick screw compressor has an oil separator nameplate, a motor nameplate, a compressor package nameplate, a screw nameplate, a relief valve nameplate, and sometimes an oil cooler nameplate. An important component of a compressor is the oil separator. The purpose of this vessel is to separate the compressor oil from the ammonia and allow only ammonia vapor to exit the compressor. Oil separators can be installed either vertically or horizontally. The purpose of an oil cooler is to cool the oil used in the compressor to ensure it doesn't overheat and break down. Oil coolers are essentially heat exchangers and take the form of shell and tube, plate and shell, and plate and frame. Compressors that are not equipped with oil coolers are equipped with a liquid injection cooling valve group, which injects ammonia directly into the compressor. We'll now turn our attention to the design codes and standards that must be adhered to during the design, installation, and operation of a compressor. Namely, we will consider unique requirements for compressors in IIAR's Design Standards, Standard 2. Then we'll examine the installation requirements in Standard 4. Finally, we will address the inspection, testing, and maintenance requirements in IIAR Standard 6. Let's start with IIAR Standard 2, which addresses the design of ammonia refrigeration systems. We'll examine the items listed on the screen, which are requirements in Chapter 8 of Standard 2. As it pertains to the design of any compressor, the minimum design pressure must comply with an earlier section of the standard, Section 5.5. The pertinent requirements here are items 1, 2, and 4. Item 1 requires that the set points of the high discharge pressure cutout and relief valves be higher than the normal operating pressure. There should be a margin between these to avoid unnecessary equipment shutdown or ammonia loss through a relief valve. Since compressors are connected to a pressure vessel in the form of an oil separator, item 2 is applicable to compressors. This requires that the compressor shall have a design pressure that is equal to or greater than the pressure relief valve set point. Provision is also provided for the compressor to be protected separately from the oil separator. Lastly, item 4 addresses compressors that are used in booster applications. These compressors discharge into the suction side of another compressor and therefore shall be considered as part of the low pressure side of the system when determining design pressure. Returning to Chapter 8 of IIAR 2, we see that specifications are provided for sizing compressor relief valves. The relief valve should be sized based on the compressor volumetric flow rate when the suction temperature is a minimum of 50 degrees Fahrenheit. In the case where a relief valve protects an oil separator and compressor, the relief valve should be sized based on whichever component has the larger relief requirement. For booster compressors, the suction temperature used in the calculation shall be the design operating intermediate temperature. A standard intermediate temperature for a two-stage system is often around 20 degrees. Carrying on with pressure relief requirements, Section 8.2.3 requires that the relief connection at the compressor be a half-inch fitting or 3/4 inch pipe at a minimum. Therefore, larger connections are permitted. Compressors must be provided with certain limiting devices, which include high discharge temperature, low suction pressure, and high discharge pressure limiting devices to shut down the compressors. Additionally, compressors should be equipped with a low oil pressure shutdown when using forced feed oil lubrication. It's important that the set point of the high pressure cutout does not exceed 90% of the pressure relief valve set point. Therefore, if a compressor relief valve has a set point of 250 psig, the high pressure cutout must not exceed 225 psig. All exposed rotating parts of a compressor must have protection in the form of either screens or guards to prevent injury. Additionally, a rotation arrow shall be cast in or permanently attached to the compressor. In regards to ultimate strength, Section 5 indicates that pressure-containing equipment must either be listed individually, listed as part of the complete refrigeration system, listed as a subassembly, designed, constructed, tested, and assembled in accordance with ASME B31.5, or designed in accordance with the ASME Boiler and Pressure Vessel Code. Compressors must also be strength tested to at least 1.5 times the design pressure, leak tested, and proven tight. Standard 2 requires that compressors be designed with a nameplate consisting of the manufacturer's name, serial number, model number, year manufactured, MAWP, and maximum rotation speed. A compressor is not allowed to be used if it lacks a nameplate. However, if the owner has documentation of the manufacturer's operating limits, the compressor may be used. The design for compressor installation must include one or more valved connections for the purpose of removing ammonia from compressors. Additionally, when a compressor is located in an area with low ambient temperature, a means shall be provided to prevent condensation of ammonia in the compressor during operation or standby. This is accomplished with an oil heater installed in the oil separator and a check valve at the discharge of the compressor. Here is an example of a check valve installed at the discharge of a compressor, which is specifically required in Section 8.5.2. Other required components for compressor installation include pressure and temperature indicating devices for the compressor and high-level float switches. High-level float switches are required to be installed on vessels that directly feed a compressor. These high-level float switches should shut down the compressors in the event the liquid level rises above a certain point in a main suction accumulator or liquid recirculator. Moving on, we'll dig into the compressor installation requirements in IIAR Standard 4. Section 4.8 requires that all equipment be positioned to ensure clearance is provided for accessibility and service requirements. Furthermore, the compressor must be protected from both physical and environmental damage. Insulated piping must not be located above electrical equipment, and when installed outdoors, equipment must be in a restricted location and have a means of preventing unauthorized access. As it relates to supporting and anchoring a compressor, any threaded fasteners must be completely engaged. The nut on the right is an example that is fully engaged. Additionally, expanded concrete anchors must not be spun after they have been set in concrete. The requirements on this page are applicable to all ammonia refrigeration equipment. Only select items pertain to compressors. Here is a quick rundown of the requirements. All equipment must be anchored and secured. Foundations and supports must be non-combustible and designed for the load they will carry. Foundations and supports must not impede drainage to floor drains. Equipment must be mounted to prevent excessive vibration. Electrical equipment must conform to the National Electric Code, and all exposed rotating components shall be guarded appropriately. Tubing smaller than 1/2 inch must be supported, protected, or both to prevent damage. This video is an example of compressor tubing that is not well supported. Now, let's turn our attention to the inspection, testing, and maintenance, or ITM, requirements for compressors. These requirements are contained in Chapter 6 of IIAR Standard 6. On a daily basis, the following items should be inspected: runtime hours, suction pressure, discharge pressure, oil temperature, discharge temperature, and the oil filter differential pressure. On a screw compressor micropanel, each of these items can be viewed on the display screen. The oil level should also be checked to ensure sufficient levels inside the compressor. Where applicable, the shaft seal leak rate of a compressor should be inspected. The leak rate will determine the state of the motor shaft seal. Here's an example of a shaft seal that is leaking oil excessively and should be replaced soon. Drive guards should be inspected on a daily basis to ensure they are still in place. This compressor is lacking a drive guard, which poses a serious safety risk. The compressor inspection table includes these final inspection tasks that should be performed on compressors on a monthly or annual basis. The testing requirements for compressors includes testing the following cutouts on an annual basis. Typical compressor cutout documentation lists the cutout set point, the type of cutout, and whether it functioned properly during the test. This video provides more details on compressor cutouts and the process of performing the testing.
A high discharge pressure cutout, or high pressure cutout as we've chosen to call it, is a safety device that must be installed on each compressor in an ammonia refrigeration system. Hi, I'm Peter Thomas, President and Senior Engineer at Resource Compliance. The purpose of a high pressure cutout is to prevent overpressurization in an ammonia refrigeration system. Should the discharge pressure in a compressor exceed the acceptable limit, the high pressure cutout will de-energize the machine, reducing the likelihood of a relief valve lifting or an equipment rupture. The International Institute of Ammonia Refrigeration, IIAR, requires that high-pressure cutouts be included in any new system design per Standard 2. Additionally, high-pressure cutouts are included as a minimum system safety requirement for existing compressors, regardless of age, in the first edition of IIAR Standard 9, which was published in 2020. Typically, high-pressure cutouts on reciprocating compressors utilize electromechanical switches, while screw compressors often employ pressure transducers. As with any safety device, it is important that high-pressure cutouts be periodically tested for proper operation. IIAR Standard 6 requires that high-pressure cutouts be tested at least annually. It should be emphasized that only qualified persons are allowed to test a high-pressure cutout. IIAR Standard 6 describes multiple approved test methods, one of which allows the cutout set point to be reduced to within the compressor's normal discharge pressure range. Keep in mind that to use this method, one must first verify that the pressure transducer reading is accurate. This can be achieved by installing a trusted gauge to ensure both the gauge and the transducer read substantially the same pressure. IIAR Standard 6 recommends that the transducer be verified at two pressures that are 10% or more apart. A successful test will de-energize the compressor, so it is important that trained personnel be available to restart the equipment after completing the test. Before testing a high-pressure cutout, make sure to notify facility management that the test will be taking place. Once approved, verify that the high-pressure cutout set point does not exceed 90% of the compressor relief valve set pressure. For example, if the relief valve set pressure is 250 psi, the cutout set point must be less than or equal to 225 psi. Using the set point reduction method requires changing the set point to within the compressor's normal discharge pressure range. Once the set point has been adjusted, the compressor will de-energize, thus concluding the test. After completing the test, the alarms can be cleared and the compressor restarted. As with all tests, it is important to document the results as necessary to demonstrate what took place. Visit our website, resourcecompliance.com, for more compliance and mechanical integrity related content.
Maintenance tasks relative to compressors includes performing an oil analysis annually or based on the runtime hours. An oil analysis report typically includes a rating which indicates the state of the oil. Here's an example of an oil analysis report that indicates the oil is in normal condition. Other maintenance tasks for compressors include replacement of shaft seals and lubrication of the compressor and motor bearings. That concludes this video on compressors. I trust you found the information useful. We have more videos on our channel about ammonia refrigeration and process safety management. Feel free to check them out if you're interested.